This one says homework 9B, problem 14, if that is meaningful to any of you. So here is the setup. For some positive constant C, a patient's temperature change T due to a dose D of a drug is given by T equal to C over 2 minus D over 3 times D squared. And the question, well, the first question is, what dosage maximizes the temperature change? So when the question says what dosage maximizes temperature change, the question that we're really asking is, or the thing we're trying to do is, we want to find the value of D that maximizes the value of the capital T. So that's what they're asking when they say what dosage, right? Dosage is D, maximizes temperature change is T. So that's what we're trying to figure out here. As we've seen a few times now, or more than a few times, right? If you want to maximize a thing, you're going to write that thing as a function of some other stuff, take its derivative to find the critical values, and then take that, or take the derivative and set it equal to 0 to find the critical values. And then those critical values might be where you have a maximum. So I want to differentiate this. So I'm really thinking here, so I have to be careful, right? C is a constant, D is a variable. So T is really just a function of D. And I think it's going to be easier to differentiate T as a function of D if we write it as, I'm trying to find my good pen here, I think this is my good one. Instead of writing it as C over 2 minus D over 3 times D squared, I might multiply the D squared through and write it as T over D, sorry, T of D. Right, I'm just writing T as a function of the dosage D. If I distribute this, it's going to make it easier to differentiate. So I can write this as C over 2 times D squared, and this is going to be D squared times D is D cubed over 3, or 1/3 D cubed. So I'm writing it as constants times variables, constants times variables to make it easier to differentiate. So now let's take the derivative. The derivative here is going to be, well, constant multiple hangs out. The derivative of D squared is 2D. So you get C over 2 times 2D minus 1/3. The derivative of D cubed is 3D squared. I'm going to set that equal to 0. I'm going to simplify. So I'm going to cancel the 2's here. I'm going to cancel the 3's here. So it looks like I've got CD minus D squared equal to 0. One answer would be D equals 0, right? If D is 0, you're going to get 0. But we can factor out a D to see if the other answer is going to be either D equal to 0 or D equal to C. So those are my critical values. Oh, which one maximizes this thing, right? So I really want to stress, this is actually a good question because it doesn't actually just give you one answer. There are two possible answers here. The dosage could be 0 or the dosage could be C. We have to figure out which of those gives us a maximum. Well, let's draw the number line. Now here's the thing. We have to be sensible about our number line here. It doesn't make sense to have a negative value for dosage, right? You can't give someone a negative amount of a drug. They said, I don't think you can. Maybe there's some weird thing where you take the drug out of the body. But typically, in a normal setting, you can't give someone a negative amount of a drug. So our number line here really should start at 0 and go like that. And here's our critical value of C. And we're trying to figure out what T prime is doing. So I pick a number. Now, this is where I've seen people struggle with this right here. Here's my derivative, and let's actually view it like this for a second. There's my derivative. And now we're trying to figure out where the derivative is positive and where the derivative is negative. So I want to pick a number that's bigger than C. Right? I want to pick something over here. What's a number bigger than C? Right? We don't really, if you don't know what C is, it's hard to think of a number that's bigger than C. There's two ways you can approach this. One way is to say, well, if I pick something bigger than C and plug it in, C minus a number that's bigger than C is going to be negative. And C is going to be positive, so a positive number times a negative number will be a negative number. A different way you can do it, if you prefer, is, well, C is positive, right? I believe they say that. Yeah, C is a positive constant in this problem. So another way you can go say, well, if C is a positive number, then 2C or double C is certainly bigger. So you can say, I'm going to pick 2C and plug that in. I plug in 2C for D, I get 2C there, and I get C minus 2C, which is negative C, which is a negative number. So you get a positive times a negative, which is negative. We can do the same sort of thing here. Pick a number less than C, either just say it's less than C, so C minus a number less than C is positive. C is positive, positive, positive is positive. Or you can say I'm going to pick half of C. C minus half of C is positive, half of C is positive, the whole thing is positive. So this is increasing before C, decreasing after C. So we do have a maximum, so maximum temperature change when the dosage is equal to the constant C. That's how we would answer this question. Okay, the second question here, the second question, I don't really know what I'm going to be doing. Let's figure out. So the second question starts off with the sensitivity of the body to the drug is defined as dT/dt. Sorry, dT/dd, the derivative of temperature with respect to the dosage. So sensitivity is other way. dT/dt, right? The rate of change of the change in temperature with respect to the rate of change of the dosage. You don't really have to know that here, but that's what they're telling us. And we found dT/dt. Oh gosh, that's hard to say. We found dT/dd. You should have picked different letters here. It's just T prime, which was that. Sorry, I wrote T prime with C here. That was a mistake. T prime was D, right? Because T is a function of dosage. So there's my T prime, CD minus D squared. And now I'm going to, well, what's the problem say? They're asking what dosage will maximize the sensitivity. So I'm going to maximize this. How do we maximize the thing? We take its derivative. We set it equal to 0. We figure out where it's increasing and decreasing. So I'm going to take the derivative of this. I'm going to take T double prime and get the derivative of this, which is going to be C minus 2D, set it equal to 0. Solve for D. Add 2D, divide by 2. And there's our candidate, right? There's our critical value. We still don't know if it's a max or a min, so let's find out. So I'm looking at what T double prime is doing now. And again, really I should be starting at 0 because it doesn't make sense to have a dosage that's negative. Here's my critical value of C over 2. So pick a number larger than C over 2, like C, and plug it in for D. C minus 2C is negative. Pick a number smaller than C over 2, like C over 4 or C over 10, and plug it in. And C minus 2 times C over 4, well, that's going to be 2, or C minus C over 2, which is going to be positive C over 2. So it's going to be positive here. That means that my first derivative is increasing over here and decreasing over here. So that means the first derivative has a maximum at C over 2. So T prime, or dT/dd, has a maximum at D equal to C over 2. It's kind of tricky. I kind of feel like there's something I should say more about here. Because, yeah, Well, there's something I'm going to say that kind of piggybacks on this. But first, I should ask you guys, are there questions about what we've done here?
For this one,
Oh, sorry, one second. Turn it up. Go ahead.
Like, the other number line, it like came out different, but like it's kind of the same formula, but it was just more of like a simplified formula, but it came out like different, if that makes sense. Like for this one, you use the CD minus D squared, and the other one you used it like a factored version.
Right. So this one, right? So you're right. So here's my derivative, CD minus D squared. And to find the critical values, I did factor out a D. Right?
Yeah.
And then I got my critical values to be 0 or C. And then when I was plugging back in, like points over here, like right here I plugged in 2C, and here I plugged in like half of C. When I plugged those values in, I could have plugged them into either version. I could have plugged them into D here or D here. But I'm going to plug them into the version where it's easier to tell if it's positive or negative. And that's usually the factored version. So I plugged it in here. When I plugged in 2C for D, I got C minus 2C, which is negative. I got 2C, which is positive, and positive times a negative is a negative. When I plugged in C over 2, I got C minus C over 2, which is positive, times C over 2, which is positive.
Oh, okay, yeah.
On the other side, right, now I'm trying to maximize the derivative. So to maximize this thing, I take its derivative and find the critical values. So there's the derivative. And the problem here is you can't really, that's actually not true. I could do some factoring here if I really wanted to. I could factor out a 2. I could write this as 2 times C over 2 minus D. That's a way I could write my second derivative. So C over 2 is my critical value. Put it on the number line. Pick a number larger than C over 2, like C. Plug in C. Oh yeah, C over 2 minus C is going to be negative. So it's negative. And then pick a number smaller than C over 2, like C over 10. C over 2 minus C over 10 is definitely positive. So the whole thing's positive. But in this case, I didn't factor it before because it was easy enough just to plug it in here because it's just kind of a linear thing. So usually you're right, I would factor, but here I didn't because it was mostly easy enough to do without factoring. But I do want to point out, this kind of brings up
I also have a question.
Oh, go ahead, yeah.
Would second derivative work here? To determine if it's maximum or minimum? So, for example, if I differentiate C minus D.
Sorry, go say that again.
Yeah.
So
yeah, the second derivative test.
Okay, so let me back up. So for this one here, you could see that C is a maximum of the original function by plugging C into the second derivative. And if you plug in C, right, T double prime of C is equal to C minus 2C, which is negative C, which is negative. So since the second derivative is negative, that means the function is concave down, which means it would be a maximum. So yes.
And for
wait, 1 sec. So yes, you can say that C maximizes this function by the second derivative test. Go ahead.
Okay, yeah, but for the second one.
So you could, but then you have to take the next derivative, right? Because to use the second derivative test for this function, which is the first derivative, you have to take the second derivative of this. So we'd actually have to take the third derivative, which is not hard. I'm just saying we have another derivative to go. So I take the third derivative, which is just going to be negative 2, right? 0 minus 2. Well, it's clearly always negative, so it's concave down. Or I should say, the first derivative is concave down. So yes, it's a maximum because of the second derivative test for that function. Yeah.
Okay.
Totally works. There was something else I want to say because people have been asked. There are people who have had some questions about there have been some interesting questions about graphs of first derivatives and kind of what they mean. So let's say I'm going to make up a graph here. Yeah, I'm going to do two examples of this because I think this is kind of worth looking at. Let's look at this example first. And we'll look at this. Yeah, let's say this is my graph. This is my first derivative. And I really want to know a couple things. I want to know, one, where does f of x have a relative max or min? Okay, so what I want you guys to first realize is that this is my first derivative. In this picture, my first derivative is always greater than or equal to 0. Right? My first derivative is always above the x-axis, so it's always greater than, I should say, it's always above or on the x-axis, right? There's a point right there. There's a point right there. So my first derivative is always greater than or equal to 0, which means I can't have a relative maximum or a relative minimum, right? To have a relative maximum or relative minimum, you guys have seen, right? To have a relative maximum, we need to have a critical value and to go positive, negative for the derivative. That's not going to happen here because the derivative is always positive. So we don't have any relative extrema. Another question we could ask is, what about critical values? And I guess I should label a few points. Let's call this point over here x1, this point x2, and this point x3. So let me ask you guys to write in the chat, how many critical values does this function have? In this interval anyway, that I've drawn. 1, 2, or 3? Guys have very good guesses. 2s, 3s, 1s, 2s. Oh, good. Good. Oh, thank you guys. Appreciate all the guesses. So I'll remind you, you get a critical value when the derivative is equal to 0. And I see 1, 2 places where the derivative is 0. So there are 2 critical values because f prime of x1 is equal to 0 and f prime of x3 is equal to 0. For those of you that said 3, I imagine you were guessing that this is also a critical value. It's not a critical value for the first derivative because it's not a place where the first derivative is equal to 0. It's going to come up in the next question, though, so don't worry. You're still right to think about that point. Yeah, you only get critical values when the derivative is 0. Okay. And then I suppose we should ask about, so I'm just going to say some things. This function is increasing everywhere, right? F of x is increasing always. And again, we know this because the derivative is always greater than or equal to 0. And now I want to ask about the second derivative stuff. Meaning, I really want to ask, where is this function concave up? And I should be more specific. I should say, where is the function f of x, which I haven't graphed, where is f of x concave up? Slash concave down. Okay, so when you're talking about a function being concave up, I don't want to say this. Okay, let's make an analogy here. I'm gonna come back to this in a second. Let's make an analogy for a minute. Whoops, let's drop the eraser. We'll really drop the eraser. Okay, so here's what I want you guys to see. We know that if f is increasing, that's the same as saying, or I should, let's make it an equal. So f is increasing is equivalent to the derivative being positive. And similarly, f being decreasing is equivalent to the derivative being negative. Well, we could also say that's true for any function, meaning if f prime is increasing, that's equivalent to the derivative of f prime, which is f double prime, being positive, right? For a function to be increasing, its derivative has to be positive. And for the derivative to be positive, the function has to be increasing. And in a similar way, if f prime is decreasing, that's the same as saying that the derivative of f prime is negative. But we know some stuff. We know that if you're saying that f double prime is negative, you're saying that the original function f is concave down. And if f double prime is positive, you're saying that the original function f is concave up. So what we can say is, oh, I can tell a function is concave up if the first derivative is increasing. I can tell a function is concave down if the first derivative is decreasing. So now, going back to our picture here, well, look, the first derivative is increasing from here to here. So this function is definitely concave up on the interval from x1 to x2 because the first derivative is increasing on the interval from x1 to x2. And in a similar way, it's certainly concave down on the interval from x2 to x3 because the first derivative is getting smaller from x2 to x3. Yeah, that's all I really want to say there. So the last thing we could say is that that means we have an inflection point at x2. And really, I mean, also x1 and x3 really, right? Because the first derivative is decreasing, then increasing, then decreasing, then increasing. So that means your function would be concave down, concave up, concave down, concave up. So we have inflection points at x1, x2, and x3. Because really, it's also concave up over here. And like pretending like this just keeps going that way. And it's also concave down from negative infinity to x1. And whenever the concavity changes, you have an inflection point. So at x1, we change from being concave down to concave up. And then at x2, we change from being concave up to concave down. And then at x3, we change from being concave down to concave up. So all those points are inflection points. So hopefully that helps with some of those graphing problems where you have to they give you the derivative graph and you have to kind of interpret what's happening with relative extrema, with inflection points, that kind of stuff. So they can be kind of weird because it's really easy to think, oh, that looks like a maximum. Well, it's not. It's a maximum of the first derivative, which is where you might have an inflection point. All right, let's do some more optimization. It just seemed like a good place to talk about the graphing stuff since we were drawing things. Let's look at this next one, which I don't have the number for, but I will still read through. This one is a little bit of a wordy problem, so let me read the stuff and I'll just write down the pertinent pieces of information. If I can even read these words. Semmelparous organisms breed only once during their lifetime. Examples of this type of reproduction can be found in Pacific salmon and bamboo. Interesting. I had no idea bamboo only bred once. The per capita rate of increase R can be thought of as a measure of reproductive fitness. The greater the value of R, the more offspring an individual produces. The intrinsic rate of increase is typically a function of age X. Models for age-structured populations of seminal Paris organisms. The intrinsic rate of increase as a function of X is given by this function. R of X equal to the natural log of L of X times M of X all over X, where R of X is the probability of surviving. This is the probability of surviving to age X. Oh, sorry, that's L of X, not R of X, apologies. L of X is the probability of surviving to age X. And M of X is the number of female offspring at age X. And then R of X is the rate that we were talking about, right? The per capita rate of increase. Per cap rate of increase. Okay. So the optimal age of reproduction is the age X that maximizes R of X. Right? We want to maximize the per capita rate of increase R because that's a measure of reproductive fitness. So we want to find the optimal age of reproduction. So we want to, so it's a lot of setups for maximize the function. So we want to maximize R of X. And they give us, I feel like they made this kind of really wonky, but they give us with L of X equal to e to the negative ax and M of X equal to bx to the c. And it's debatable whether or not you want to plug those in right away or not. And I'm really not sure. Yeah, so I know I want to maximize this. So I want to find R prime to equal to 0. And I have some ideas here. I'm just not sure if they're all good. Okay, I think we should simplify this first. Here's what I think we should do. I think we should rewrite R of X using a logarithm rule. I can rewrite this as the natural log of L of X plus the natural log of M of X all over X. That seems like it's going to be easier to differentiate because I won't have to use the product rule at least, right? I won't have to do 1 over L of X times M of X times the derivative of that, which is the product rule. So usually I think it's a good idea, not always, but most of the time, to simplify your function if you can before you differentiate. And now let's go ahead and plug these in. So I've got the natural log of e to the negative ax. That's going to simplify really nicely. Plus the natural log of bx to the c. That's not going to simplify quite so nicely, but there's something we can do. Over x. Okay, natural log of e to the negative ax is just negative ax. And the natural log of bx to the c, I can't bring down that power yet, but I can write it as plus the natural log of b plus the natural log of x to the c. And then I could bring down that power of c. So here's all my simplification. My function, sorry, that's an x on the bottom, not an r. So I've got a negative ax plus a natural log of b plus a c times natural log of x all over x. All right, let's differentiate this thing. I think I can erase this up here. It seems not too bad. Okay, so I'm going to take the derivative of that. r prime. So I am going to use the quotient rule. It's going to be the bottom times the derivative of the top. The derivative of negative ax is negative a, right? Because a and b are both constants, and c, right? A, b, and c are constants. Okay, somebody tell me, what's the derivative of the natural log of b?
1 over b.
I tricked you. Or you could say it's 1 over b times the derivative of b, which is 0, right? So natural log of b is a constant, and so its derivative is going to be 0. Thank you for answering. I really appreciate the wrong answers. Thank you for answering, because they help me point out things that everyone might be missing. So I appreciate the brave wrong answers. All right, c times natural log of x, the derivative is going to be c times 1 over x. Okay, we did bottom derivative of the top. Now we have to do minus the top times the derivative of the bottom, which is just 1. So it's just going to be minus the top. So it's going to be minus ax plus natural log of b plus c natural log of x. All divided by x squared. And we're trying to find the critical values to maximize the, to find the maximize Rx. Okay. Interesting. Yeah. Okay. That's a good point. So let's simplify this. I'm going to distribute the x here. So I'm going to x times negative ax, and then x times c times 1 over x is just plus c. And then distribute the minus sign here, so I get a plus ax, a minus natural log of b, and a minus c natural log of x. Whew. This is looking terrible. All right, we can cancel a negative ax and a positive ax. And I think that's kind of it. So then we're going to set the whole thing equal to 0. Okay. So if I set a fraction equal to 0, I'm really just trying to find where the numerator is equal to 0, right? Because that's how a fraction is 0. You get 0 divided by not 0. So I'm going to really just set this top, which is c minus natural log of b minus c natural log of x equal to 0. So I'm going to try and solve for x. Well, that's not too terrible. I'm just going to isolate the x part. And I'm going to run out of room. So I'm going to get c minus natural log of b equal to c natural log of x. Divide both sides by c. So I get 1 minus natural log of b over c equal to the natural log of x. And then finally exponentiate both sides. So that e to the all of this equals x. Now, as I've said a couple times, we found the critical value. Does that mean it's a maximum? Not necessarily, right? We don't actually know it's a maximum until we check. So you have choices here. As I don't know who was pointing out, but we could use the second derivative test. Taking the second derivative here might not be insanely terrible. I don't really want to do it though. It could be fine, it could be awful. Or we could use the first derivative test. Let's talk about using the first derivative test. So here's my first derivative. R prime of x is c minus natural log of b minus c natural log of x all over x squared. And I guess technically 0 is a critical value as well, or at least it's kind of the end of the domain, right? It doesn't make sense for x to be negative because x is the age. So here's our number line where here's our critical value, which I'm just going to call my critical value, right? I don't want to write that number there, but that's what's going right there. And then I want to pick a number bigger than that. That's terrible. How do I pick a number bigger than that when I don't know what b or c is? Well, I need to check one thing. A, b, and c are positive. That doesn't even, yeah, it could be kind of it. So So although I said I didn't want to take the second derivative, I might be kind of stuck. So here's what I should really say. Obviously, this is the only answer, right? This is a web work problem. This is the only critical value we got. This is what you're going to jam in there. Now, I should point out, the question specifically asks for the optimal age of reproduction, meaning they're not asking for what you get when you plug this back into the function r. They're asking for what the value x is. So this is the answer we are looking for. I'm not going to do it because I don't think it's really worth our time, but you could take the second derivative here, plug this in, and show that the second derivative is negative, which would mean you have a maximum. But I don't think that's a good use of our time, so I'm not going to do that. Other questions or any questions about this?
I have a quick question about when you were finding like the derivative. Why is x out of the parentheses?
So I'm using the quotient one. So I know I erased like the function, right? Let me remind you. The function, after we'd simplified it, our function had simplified to, let me look at it again. Sure, it was x on the bottom, and it was a negative ax plus natural log of b plus c natural log of x. Right, this was the function that we were differentiating. So when I differentiated this, I got the bottom.
Oh, yeah. Okay, that makes sense. Yeah, makes sense now.
Good. Anything else? Other questions? Okay. Got one more optimization problem, or at least I think it's an optimization problem that someone sent, and then I think we will start talking about L'Hopital. So for a fish swimming at a speed v relative to the water, so v is our speed, the energy expenditure per unit time is proportional to v cubed. Okay, so I'm always like trying to write the equation because when I took calculus, it was always like my job usually be like, here's the equation I'm trying to set up. So I'm thinking, oh, I hear that, I'm getting, okay, E is proportional to, meaning it's a constant times v cubed. But they're totally giving us that later on. So we don't need to work quite so hard. It is believed that migrating fish try to minimize the total energy required to swim a fixed distance. If the fish are swimming against a current, U, where U is less than V, then the time required to swim a distance, L, is L divided by V minus U. And the total energy required to swim the distance is given by, so they just give us the equation. They give us that E of V, right, the energy required to swim and the velocity of V, right? Cool. Is equal to AV cubed times L over V minus U. Where A is the proportionality constant. Determine the value of V that minimizes E. And I should point out, constant, right? All those things are constants. U is the current that we're swimming against. So that's some set value. V is the velocity that the fish is going to swim at. That's a variable value. So I want to minimize this. And although you could use the product rule, I think it probably makes more sense to rewrite this as LAV cubed over V minus U. Because I'm going to have to use the quotient rule anyway to take the derivative of this part, so why don't I just write it as a quotient in one quotient? So I want to find the value of V that minimizes this. So let's take the derivative. So for all the words that they've given us, so it is important to read these questions, right? You have to kind of read the question to know what they're actually doing, but we probably could have gotten away with reading like the last 3 lines of this. E is the function, A is the proportionality constant, and the question is determine the value of V that minimizes E. everything that comes before the equation, although important to understand what's actually happening, you don't need to know to do the math. So let's take the derivative. E prime of v, let's see, it's going to be the bottom times the derivative of the top. The derivative of the top is a constant times 3v squared. Minus the top times the derivative of the bottom, which is just 1, all over the denominator squared. Now be careful. It's very tempting to want to cancel a v minus u with a v minus u. We can't do that unless we can factor out a v minus u from here and here. And there isn't a v minus u to factor out from here, so we can't cancel a v minus u. So we have to work with the top. And again, we're trying to set this equal to 0. When I'm setting a fraction equal to 0, I'm really just thinking about where the numerator is equal to 0. So let's simplify the numerator. I've got v minus u times 3lav squared minus lav cubed. I want to solve for v, right? Because v is my variable. So I probably should distribute this here. So I'm going to take this and distribute it to each of these terms. So I'm going to get v times this is going to be 3lav cubed minus u times this is going to be 3lauv squared minus lav cubed equals 0. I can subtract these from each other, right? 3 lav cubed minus 1 lav cubed is 2 lav cubed. So I've got 2 lav cubed minus 3 lauv squared. And I would factor. What can I factor out from each of these? There's like a lot of answers here. There are 3 things I can factor out.
LAV
squared. Yeah. So I can factor out an LAV squared. I'm left with a 2V here. I'm left with a 3U here. So I'm going to solve for V. So either V could be 0, which again doesn't really make a lot of sense because V is the velocity the fish is swimming at. 0. So often reading the problem gives you some context for what kind of critical values might make sense. And then here, if I set that equal to 0, I get 2V equal to 3U. So V is equal to 3/2 U. So the speed that the fish swims that's going to minimize energy expenditure, at least we think it'll minimize it, would be 3/2 or 150% of the current that you're swimming against. Interesting. You could show it's a minimum by either taking the second derivative or by trying to use the number line. Here, I think the number line is a little easier to use. So if I look here, right, this is, so let me write what my second derivative is, simplified. Here's the numerator of my second derivative. Sorry, my first derivative. I haven't gotten the second derivative. I'm going to rewrite my first derivative as, so here's the numerator simplified. So it's LAV squared times 2V minus 3U over V minus U squared. There's my first derivative. If I want to check that this is actually going to give me a minimum, here's my number line. Again, I'm starting it at 0 because it doesn't make sense to have values less than 0. So pick a number bigger than 3/2 U. I'm going to pick 2U or 100U, right? Pick just something insanely big. So if I pick 100U for V, well, let's see. LAV squared is all positive, and 200U minus 3U is positive because U is a positive number. Pick something less than 3 halves u. How about 1u? If v is u, then I get L times A times u squared, which is positive, 2 times u minus 3 times u, which is going to give me a negative u, which is negative. Oh, I didn't say before, but clearly the denominator is positive because it's something squared. So that's going to be negative. So it is decreasing, increasing, which means we have a minimum there. Great. Now, I will again point out, you probably don't have to check this if it's a web work problem, because they're just asking you to plug in the value. Since we only got one value, it's clearly the only candidate to put into the response anyway. But in general, it is kind of important, especially if you have more than one critical value, to see which one's a minimum, which one's a maximum, if they're asking for a specific thing. But most of the time with optimization problems, usually you're going to get the thing they're asking for. Meaning if they ask you to find something that minimizes your function, you're going to find a thing that minimizes your function. You're not going to magically find something that maximizes it. But just be aware that technically it is important and necessary to check to see if the critical value you found actually is giving you a minimum of your function. Okay, so I think that's enough of that. Let's talk about L'Hopital's rule. Now, the nice thing about L'Hopital's rule is that it's most of the time, or a lot of the time, pretty straightforward to apply. So here is the setup. And actually, let me grab one thing so I want to make sure I'm saying the words exactly how I want to say them. Oh, come on, mouse. Why is that mouse being all weird? Sorry. Oh, let's see. Is this the one I want? Let's see. Sorry, one sec. There we go. Yeah. So here is L'Hopital's rule. And you should say L'Hopital. You should not say La Hospital. If you say La Hospital, that's okay. But it's a French name, so L'Hopital. So L'Hopital's rule goes like this. If the limit as x approaches a of some function f of x divided by some other function g of x happens to be a specific type of indeterminate form, if this is a 0 over 0 or an infinity over infinity, then, well, we don't know what that is, right? 0 divided by 0 could be 17, right? 0 goes into 0 17 times, right? I mean, right? Let's see, 0 divided by 0. 0 goes into 0 one time, 17. Yeah, 17 times 0 is 0. Subtract. Check, right? It works. Obviously, I'm being facetious here, right? I could have picked any number there. Could have been 17. It could have been a billion. It could have been -2. It could have been pi. So the point here is that 0 over 0 can be anything. That's why it's called an indeterminate form, because it is undetermined what it actually is. It can end up being anything depending on what your functions are. Same is true for infinity over infinity. Infinity over infinity can have any value. As big as infinity, as small as 0, negative infinity, 2, whatever. So if you have something that looks like this, specifically a fraction that's a 0 over 0 or infinity over infinity type, then, and only then, you can say that, well, this limit, as x approaches a, of f of x over g of x, has to be equal to the limit as x approaches a of f prime of x over g prime of x. So basically, the limit of the quotient of the functions is equal to the limit of the quotient of the derivatives of the functions. And I should point out, this is only true if it exists. Right? If this limit doesn't exist, then we can't say that this limit is equal to that limit. Okay, so I think there's so we're not going to prove this. It's kind of hard to prove, but I do want to kind of give you some amount of intuition as to why this is actually true. So let's look at kind of a kind of an interesting, I don't want to say example really, but an interesting situation. So, yeah, I feel like the setup's the best. Imagine we have two cars. Imagine there are two cars. Let's call them car A and car B. And we know the following. Car A, two cars A and B, and they are traveling for an infinite amount of time. Which I know, like, not for real, but, you know, that's why we are imagining. So we've got, like, car A, and I can draw a car, kind of. This is your math teacher car. Right? Here's car A, and here's car B. Okay. And let's say that A of t equals the distance the car A has traveled. And the derivative, well, we know that the derivative of distance is velocity or speed. So, and the same thing for B. We're going to say that B of t is the distance the car B has traveled, and B prime of t is the velocity that car B is traveling at. Now, and this is kind of the important part, let's suppose that car A travels twice as far as car B. So they go forever and ever and ever, and at the end of forever, car A has gone twice as far as car B. Okay, there's a mathematical expression I can write to kind of show that. That would be saying the limit as t goes to infinity of A of t over B of t. Well, I'm saying the distance that car A traveled divided by the distance that car B traveled. If car A traveled twice as far, then its distance divided by car B's distance should be equal to 2. But now, think about this. If car A traveled twice as far as car B in the same amount of time, how much faster must car A have been going? Well, it kind of makes sense that car A had to be traveling twice as fast. Right? It makes sense that the velocity of car A was 2 times the velocity of car B. Right? If I went twice as far as someone in the same amount of time, then I was going twice as fast as them in that same amount of time. So we could say, well, then it kind of makes sense that the limit as t goes to infinity of the velocity of car A divided by the velocity of car B also has to be 2. For car A to travel twice as far as car B, car A has to travel twice as fast as car B. So this is not a proof by any means, but this is kind of an idea to be like, oh yeah, this kind of makes sense, right? If the limit of a quotient is equal to a number, the limit of the rates of changes of those, or the quotient of the rates of changes of those things also has to equal that same number. And again, this is only true for indeterminate forms, right? You can't do this for fractions that are just like whatever. So that's kind of the idea. If that means something to you, great. If you're kind of like, what is James talking about? That's also okay. You don't have to get this to be able to use L'Hopital's rule. I just kind of wanted to give you guys some sort of intuition or understanding about what is happening, why it might be true. So let's look at some examples that we know are true. Yeah, so let's look at, say, the limit as x goes to infinity of 6x squared plus 11 over 2x squared plus 1. All right, so we know how to evaluate this limit without using L'Hopital's rule. In fact, I bet you guys all know the answer to this limit already. Anyone want to tell me?
Infinity over infinity?
That is true. That's a fair point. This is definitely an infinity over infinity type. But I think you guys know a rule for how to take the limit as x goes to infinity of a rational function where the degree on top and the degree on the bottom are the same.
3.
3, right? Because when the degrees are the same, it's the quotient of the leading coefficients. And really, the work you're doing there, or the work we used to do, is you divide everything by the highest power of x in the denominator. So you could do this as its limit as x goes to infinity of 6x squared over x squared plus 11 over x squared, 2x squared over x squared plus 1 over x squared. And that becomes the limit as x goes to infinity of 6 plus 11 over x squared over 2 plus 1 over x squared. This goes to 0, this goes to 0. You get 6 over 2, which is 3. Not that you need to show this work, but that is the work we used to do. You're perfectly fine if you just said 3. However, you could also use L'Hopital's rule. I appreciate whoever said infinity over infinity. It's very important that we mentally check that it is a 0 over 0 or an infinity over infinity so that we can actually use L'Hopital's rule. And it definitely is, right? The top is going to infinity, the bottom is certainly going to infinity. So I can use L'Hopital's rule. And when I use L'Hopital's rule, I like to write a little L apostrophe H above my equal sign to let the person know that I'm using L'Hopital's rule. I'm going to take the derivative of the top, which is 12x. I'm going to take the derivative of the bottom, which is 4x. And in this case, I'm going to cancel the x's because I can. And then the limit of 12 over 4, well, the limit of a constant is just the constant. But that's just 3. So in this case, infinity divided by infinity was 3. This infinity was 3 times as big as that infinity. Or this part grows 3 times as fast as that part grows, is another way of saying that. And that's really true for any of these rational function examples, right? If I wanted to find, say, the limit as x goes to negative infinity of 5x squared plus 6x plus 1 over 7x squared plus 3x minus 2. While we know the answer is 5/7, we could also show it using L'Hopital's rule. And again, I can do that because I have an infinity over infinity. Oh, do I have an infinity over infinity? Is the top going to infinity? It is. Because even though x is going to minus infinity, this part's going to infinity, this part's going to minus infinity, but since this one's to a higher power, it's outgrowing this one that's to a lower power. So yes, the top's going to infinity, the bottom's also going to infinity. I should mention, you can have any type of infinity over infinity. Meaning, if I put a -7 here, that would be okay. You can use L'Hopital's rule if you have infinity over infinity, infinity over negative infinity over infinity, or negative infinity over negative infinity. Any type of infinity over any type of infinity is okay. You're allowed to use L'Hopital's rule. So in this case, now the limit's going to be 5 over -7 or -5/7. I'm going to use L'Hopital's rule. So let's see, the derivative of 5x squared is 10x, the derivative of 6x is 6. Here at the bottom is going to be -14x plus 3. And now I do, that's a 6, not a 6x, sorry. And now I do need to use L'Hopital's rule again, because I've got an infinity over a negative infinity over a positive infinity. Right, the top's going to negative infinity because x is going to negative infinity, and the bottom's going to positive infinity. And I thought I heard someone start to ask a question. Was there a question? Okay, no question. So using L'Hopital's rule again, take the derivative of the top, which is, limit of x goes to minus infinity. Derivative of the top is 10, derivative of the bottom is -14, and 10 divided by -14 is just -5/7. So L'Hopital's rule certainly works for this example that we already knew the answer to. Great. It's good that the thing that's supposed to work works. Let's look at a couple more examples that we already kind of know the answers to. Here's a couple 0 over 0 types. So here's, let's do the limit as x goes to 4 of x squared minus 16 over, what do I want? I want x squared minus 5x plus 4. You could totally do this the old way, right? You could totally do this by factoring. It's x minus 4 times x plus 4 on the top. On the bottom, it's x minus 4 times x minus 1. You cancel the parts that are making it 0 over 0, right? It is a 0 over 0. If you plug in 4, you get 0 on top. You get 16 minus 20 plus 4, which is 0 on the bottom. But then after you cancel these, you can plug in the 4, and you can get 4 plus 4 over 4 minus 1, which is 8/3. But you could also use L'Hopital's rule. Say, well, I'm going to take the derivative, right? It's 0 over 0. Let's do the derivative of the top and the bottom. I should really be careful, right? We're not taking the derivative of the whole thing, right? That would require the quotient rule. We're taking the derivative of the top part and the derivative of the bottom part totally separately. So the derivative of x squared minus 16 is 2x. The derivative of x squared minus 5x plus 4 is 2x minus 5. Now be careful, we can't use L'Hopital's rule again here, right? I don't have a 0 over 0. Really what I should be saying is every time after you use L'Hopital's rule, you should check, can I plug this in and get a real number? And if I do, I do. Right? If I plug in 4, I get 2 times 4 over 2 times 4 minus 5, which is 8 over 3. Same. Great. And here's another example. One that I know a lot of you wanted to use L'Hopital's rule for way back when. The limit as x goes to 0 of sine of x over x. Also a 0 over 0 type. Sine of 0 is 0 and 0 is 0. So if I use L'Hopital's rule here, well, I should say, first of all, what do we know this limit is equal to? Maybe we forgot. It's okay. We can use L'Hopital's rule. Yeah, definitely 1. But it's really easy with L'Hopital's rule, right? We can say, okay, that's the limit as x goes to 0. Derivative of sine is cosine. Derivative of x is 1. And then I can plug in 0 and get cosine of 0 over 1, which is 1 over 1, which is 1. So it totally works. It also works for things that we actually need it for, right? So these are all examples that we could have done without L'Hopital's rule, but there are plenty of functions where we actually do need L'Hopital's rule. For example, how about the limit as x goes to infinity of e to the x over x squared? Top's going to infinity, bottom's going to infinity. So let's use L'Hopital's rule. Some people, when they do these, they like to write that it's like infinity over infinity to remind themselves what's going on. I don't typically do that, but you're certainly welcome to. So let's see, if I take the derivative of the top, it's going to be e to the x. The derivative of the bottom is going to be 2x. If I try plugging in infinity, it's still infinity over infinity. So I do it again. A lot of times you use L'Hopital's rule multiple times. So doing it again, all right, let's write the L apostrophe H here. The derivative of e to the x is still e to the x. The derivative of 2x is 2. Can I use L'Hopital's rule again? Is this an infinity over infinity? It's not. So at this point, I have to think about what I have. The top is infinitely large. The bottom is 2. Infinity divided by 2, still infinity. So this limit is infinite. And what this is showing us is that e to the x outgrows x squared. In fact, e to the x outgrows any power of x. If I was going to, in the same sort of way, ask, what's the limit as x goes to infinity of, say, x cubed over e to the x, I'm pretty sure I know what's going to happen here. I know that e to the x is a way bigger thing eventually than x cubed. I know that if I keep taking the derivative of the top, eventually the derivative of this polynomial is going to be a constant. That's true for any polynomial. For any positive integer power of x, if you take enough derivatives, you get to a constant. Whereas with e to the x, the derivative is always e to the x. So I know that after so many steps, I'm going to get to a place where the denominator is still e to the x, and the numerator is some constant, which means this one's going to be 0. And the steps would be, right, the derivative of the top is 3x squared, bottom e to the x, and then do it again, right, because it's still infinity over infinity. Limit, you have to write the limit each time, right? You're taking a limit here. You only ever use L'Hopital's rule when you're talking about limits, right? Never for like just a derivative or anything. It's only for a limit. Let's see, derivative of the top is 6x, the derivative of the bottom is e to the x. Still infinity over infinity, so I do it one more time, and now the derivative of the top is 6, and the derivative of the bottom is e to the x. And a constant divided by something that's infinitely large is going to be 0. So both of these examples show how e to the x is a much bigger thing than x to any power. And in a similar way, someone could ask you, not to show, because you wouldn't want to show all the steps, but someone could say, hey, what's the limit as x goes to infinity of x to the 1,000th power divided by e to the x? Well, we know that after we take the derivative 1,000 times, we're going to, or I should say, we know that after we apply L'Hopital's rule 1,000 times, the top is going to be 1,000 times 999 times 999. It's going to be 1,000 factorial over e to the x. Right, so you do this enough times, you're going to get the limit as x goes to infinity of 1,000 times 999 times 998 all the way down to 2 times 1, which is 1,000 factorial, which is a really big number. It's still a constant. The denominator is not a constant. It's something that's infinitely large. So this is also going to be 0. So e to the x is way bigger than x to the 1,000. Now, if you graph x to the 1,000th over e to the x, it'll start off being really, really big. In fact, let's take a look. It's kind of a good idea. It might be a good idea. It could be a terrible idea. Let's see if it's a good idea. Sorry, let me show you guys here. It's kind of cool to see things. Sure. So let's graph y equal to. I'm going to go with x to the 1,000th, and then we'll see if that's really stupid. So it looks really, really big, right? It's like, holy smokes, that's super big. But if we go way far out, no, it's like, no, I picked a number that's too big. It's like, good luck, James. I could probably do something, but let's just make the power slightly smaller. Let's try that again. Wow, it really does. So I know you guys are not believing me because like, okay, look, this one you can see it. So, right, it starts off getting super big and then eventually the e to the x overpowers it and it comes back down. That would be true if you picked any power of x. You would just have to go way, way, way zoomed out on your graph to actually see it happen for like x to the 100th. So 100 was a bad choice. 1,000 was a really bad choice. But hopefully you can kind of get the idea here, like, oh yeah, no matter how powerful that is, right, eventually it's going to come back down. Well, that's kind of fun. So yeah, look, I mean, it looks dumb, but right, eventually it's coming back down. It's kind of cool. So if you look in here, and you can see like, yeah, eventually this fraction, it's like, ooh, getting super small. Yeah, kind of neat. All right, anyway, enough of that. Let's do some more, because there's lots of other types of things you can look at with L'Hopital's rule, like the following. Where'd you go? Sorry, I had a bunch of examples and I've lost them all. Oh yeah, okay, so how about the limit as x goes to infinity of the natural log of x over x squared? Okay, well, first things first, is this an infinity over infinity type or a 0 over 0 type? Yeah, it's infinity over infinity. The denominator is definitely going to infinity, and we've seen the graph of natural log of x. We know that it goes to infinity as x gets bigger and bigger and bigger. So this is infinity over infinity type. So we're going to use L'Hopital's rule. The limit as x goes to infinity. The derivative of natural log of x is 1 over x. The derivative of x squared is 2x. Now this is no longer an infinity over infinity or a 0 over 0 type. And more specifically, when you get to this place where you have just powers of x after you've used L'Hopital's rule one or more times, you typically want to try and simplify this. So I can rewrite this limit as the limit as x goes to infinity of 1 over x times 1 over 2x, which is just the limit as x goes to infinity of 1 over 2x squared, which is definitely 0. So just like an exponential always overpowers a power of x that's positive is always going to outpace a natural log of x. It's interesting. One other thing I want to look at is, so let's say I want to look at the limit as x goes to 0 from the right of the natural log of x over x. Well, I'm going to make a mistake. I made a mistake. I used L'Hopital's rule, which was the mistake here. Because this is not a 0 over 0. As x goes to 0, the natural log goes to negative infinity. Remember, the graph of the natural log of x looks like this. As we get closer and closer to 0, the graph goes down to negative infinity. So I actually couldn't do this. It's not allowed because I don't have the right type. This is a negative infinity over 0. Well, actually, I can just kind of evaluate what that is, right? If this is a negative infinity over a small positive number, okay, somebody tell me, sorry, I've got the chat covered up. What's a really big negative number divided by a really small positive number going to be? Well, is it positive or negative? See, negative divided by positive, definitely going to be negative. And is it really big or really small? Sorry, that's not a good question. Is it really negatively big or really close to 0?
Negatively big.
Right, because it's a really big thing divided by a really small thing, which makes it really, really big. It just happens to be negative. So typically when I say really small, I mean really close to 0. If I'm trying to say really negative, I'll say negatively big. So yeah, so this one we can just say, hey, it's super negative thing over super small positive thing. It ends up being super negative. All right. We're almost out of time. Let me see. Is there another example I really want to do? So we'll talk more about L'Hopital's rule next time as well, because I think it's worthwhile. Because there are some other types of things. In fact, yeah, let me do one. Let me give you a preview of what I want to talk about next week. Not just this, but this is what we do. So let's say I want to find the limit as, what's a good example here? Sorry. Sure. Not you. Fine, we'll do this one. Limit as x goes to infinity. I don't want infinity, really. I want 0, I guess. Yeah. 0 of x. Now let's do the square root of x times the natural log of x. So first of all, I definitely can't use L'Hopital's rule yet. They don't even have a fraction, right? This is not a fraction. You can't use L'Hopital's rule if you don't have a fraction. Specifically, a 0 over 0 or infinity over infinity type of fraction. But I will point out that this is a 0 times infinity type, which is another indeterminate form. It can be anything. It could be 0. In fact, this one is going to be 0, but it could be 2, or it could be 7, or it could be a million, right? Or it could be infinity. So when you got, right, because this isn't really 0, it's close to 0. So when you've got a very small thing times a very large thing, it's really unclear what you end up getting. It could end up being 0, right? The small thing might be small enough that it overpowers the big thing, or it might be really, really big, depending on if this thing is big enough. So here we have a 0 times infinity. Let's see what happens. Well, let's see, what can we do? So we have to rewrite this. I'm going to rewrite this as the natural log of x over the reciprocal of that. 1 over the square root of x. Now it's a negative, oh, sorry, I should say the top is a negative infinity, right? Because natural log goes to negative infinity. Still an infinity times 0. So now I've got an infinity over an infinity, because 1 over 0 is infinitely large. So this is an infinity over infinity type. So we can use L'Hopital's rule now. So that's often the plan of attack, is to take something like this and do some algebraic work to make it look like a fraction that's either infinity or 0 over 0. So let's use L'Hopital's rule here. Sorry, that's a 0. And let's be smart about this. Instead of writing this as 1 over the square root of x, let's write that as x to the negative 1/2. So now, using L'Hopital's rule, the root of the natural log of x is 1 over x. The root of x to the negative 1/2 is negative 1/2 of x to the negative 3/2. Okay, I really, now that I've got powers of x over powers of x, I want to simplify. So I'm going to rewrite this as the limit as x goes to 0 from the right. I've got 1 over x. Instead of dividing by negative 1/2, I'm going to multiply by its reciprocal, which is going to multiply by negative 2. Instead of dividing by x to the negative 3/2, I'm going to multiply by x to the positive 3/2. Okay, x to the 3/2 divided by x is just x to the 1/2. So I get the limit as x goes to 0 from the right of negative 2 times x to the 1/2, which is just the square root of x. Plug in 0, square root of 0 is 0, 2 times 0 is 0, you get 0. And that's it. So in this case, it happens to be that a 0 times something infinitely large ends up being 0. But I will show you next Tuesday other examples where a 0 times something infinitely large is not 0. It ends up being 1 or bigger. So yeah.